So that's a pH probe. It's dreadful. We only use it because we have to, and you need to calibrate it all the time. Anybody worked on any of those? Any questions on pH? Okay, next thing we're going to... we've gone on to millions of miles. Right, we're going to go on and do conductivity is the next thing. Conductivity is the opposite of resistance. Now, I'm assuming you all know what resistance is, and you all know how to measure resistance. Is that a yes or a no? Right. Conductivity is the opposite of resistance, and we measure it the same way. Basically, a piece of copper wire, for instance, has got a low resistance and a high conductivity, whereas a piece of wood has got a high resistance and a low conductivity. So this is what conductivity is. It's the opposite of resistance, or resistivity. Conductivity, units of conductivity is the very unfortunate name Siemens. So you measure conductivity in Siemens. And when you're measuring conductivity, you have to make sure that your Siemens don't get discharged. So, when we're measuring the conductivity of liquids, other things that are important is how far apart we're basically going to use a mega. We're going to mega a liquid. Things that are important is how far apart are the mega probes and how big is the surface area of the mega probes, because that's going to make a difference to the measurement of conductivity. So we have a couple of probes, we stick a high voltage across the two probes and we measure the current that flows. Conductivity probes look like this. The temperature of the liquid is going to make a big difference, so we also need to measure the temperature and compensate for the temperature. The reason we measure conductivity is because, well, I'll ask you a question. How good a conductor is pure water? Pure distilled water. How good a conductor is it? Yep, that's right. Pure water is a very, very good insulator. So we'd say that pure water has got high resistance, low conductivity. Now, the dirtier you make water, the better it is at conducting. So we can use conductivity as a measure of pollution, of impurity in water. Because if we go down the scale, ultra pure water, very, very low conductivity, very high resistance or resistivity. Pure water, which is stuff we might want to drink, that's got a resistivity of about 10 megohm centimeters, or conductivity of 0.01 microsiemens. And the dirtier the water becomes, so that if we get down to wastewater or brackish water, salt water, we see that salt water has got quite a low resistivity, about 100 ohms. So if you wanted to measure the purity of water, the easiest way to measure the purity of water is to measure the conductivity of water. So it's just a simple mega. That's all a conductivity sensor is. It's a simple mega. We use it for measuring things like swimming pools. We want to know how impure a swimming pool is because the impurity in a swimming pool is normally chlorine. And we want to know how much chlorine we have in the water. rivers, we want to measure the impurity of rivers. It gives us a measure of the salinity of a river, which, as you know, is a very big issue in Australia. And wherever we're using water for process, if we measure the conductivity, we get a measure of how much we are polluting that water. Now, I'm going back. The conductivity sensor is, to all intents and purposes, a mega. As far as call-outs go, what do you reckon the main call-out to a conductivity sensor is? The main breakdown? You're all right, but there's one thing that you do get called out for all the time, and that is the battery goes flat. I know that might seem silly, but the thing eats batteries like you wouldn't believe. Battery goes flat, and you get called. The next thing that happens is, you are correct, the probe starts to break down. And if the probe starts to break down, you change the probe. But if you're changing the probe every 2 or 3 weeks, the next thing that breaks down is the plug that the probe plugs into. And then the next thing that breaks down is the lead coming out of the plug that the probe plugs into. And that's the sort of breakdowns you'll be on with a conductivity sensor. Silly little things. The next thing we're going to look at, the next type of analyzer, dissolved oxygen. Now, dissolved oxygen is oxygen that's dissolved in water. It's very important to have oxygen in water because fish are oxygen breathers. And animals like fish and shrimp and krill and all those good things, they all need to breathe oxygen in through their gills. If there isn't oxygen in the water, then those animals die out. And the aerobic plankton, what are they called? The small single-cell aerobic algae die out as well. And when they die out, the anaerobic algae move in. And unfortunately, our anaerobic algae tend to be a wee bit poisonous. So it's very important that we know how much dissolved oxygen there is in a river. There are 2 ways of measuring dissolved oxygen. The first method is basically the same method as the pH sensor uses. You have a special glass probe which is permeable to oxygen ions, and you measure the oxygen ions going into it. This works every bit as well as the pH probe does. It's every bit as reliable, and it needs every bit as much calibrating. That's the first method, and despite my sarcasm, you might have noted I don't like these type of probes. They are oversensitive, and they're just a pain. The other method of measuring oxygen is a thing called ionic mobility. Now this relies on the fact that if you put a big magnet on ions, you can shift them around, and then you can detect them moving. So you get this thing called the electrodeless cell. And the electrodeless cell looks like this. It's nowhere near as accurate as the glass cell. But the fact is that you can get one of these and chuck it in the back of your ute, drive down the road, check a river, chuck it in the back of your ute, drive to another river and check that, and it will still be working. So the electrodeless cell is a much better way of measuring dissolved oxygen. Now we're going to look at some other things, gas analysis. Gas analysis is very important to us nowadays because of all the pollution that has occurred in the past. So we're going to analyze gases. We're going to analyze gases coming out of chimneys, and we're going to analyze gases just sitting around in rooms. The first thing I'm going to look at is the stack gas analyzer. This is a gas analyzer on a stack. Now, the first thing you need to be aware of with a stack gas analyzer is that it's halfway up a chimney stack, which is not a great place to be. As an instrument person, it'll be your job to go up there and look after the stupid thing and get it working. One of the first types of gases we need to measure is the amount of oxygen in the gas. For this we use a zirconium cell. Zirconium is a special mineral that's mined, it's normally mined at the same places as you find diamonds. It looks very like diamond. It's a clear mineral, and the funny thing about zirconium is that oxygen can pass freely through it. So you build a thing called a zirconium cell, and you put pure oxygen on one side and whatever you're measuring on the other side, and you measure how many of the pure oxygens move from one side to the other. This is what it looks like. Here's another picture, and here's a picture. Down here is a picture of a real life one. First problem with a zirconium probe is that you have to put pure oxygen on one side, which means you need an oxygen bottle somewhere along the lines. Oxygen is very nasty stuff. If you have anything and any type of ignition source and oxygen, then you will have a fire. Virtually anything burns in pure oxygen. Steel burns in pure oxygen. So oxygen is quite unpleasant, and it's an oxygen bottle which you, as the instrument person, will have to maintain. So it's just another picture of how the zirconium oxygen analyzer works. We have pure oxygen on one side, we have the flue gases on the other side, and we measure the voltage across the zirconium cell. Another method of measuring flue gases is by using absorption. You see, different gases absorb different frequencies of light. So if you have a very strong light source and you shine it through a gas, then you will be able to see what is being absorbed, and by what is being absorbed you'll be able to see what gas is present. There's a few different ways of doing this. The first one is to use a laser as a light source, a very, very strong laser. And we shine that laser through and we look to see how much of the light is absorbed. Different things absorb in different frequencies. Carbon dioxide is absorbed here in around about the 4.2 nanometer wavelength. So carbon dioxide absorbs infrared light in the 4.2. Carbon monoxide absorbs infrared in the 4.6. Propane, for instance, absorbs infrared in the 3.4. So if we shine a light through the gas and we look to see what's being absorbed, we can from that work out what's in the gas, and we can work out what's going up the chimneys. Nowadays, the Environmental Protection Agency are very keen to make sure that we don't put lots of nasty stuff up the chimneys.